Section 3.1, Derivatives of Polynomials and Exponential Functions. This actually starts off a couple of sections of looking at some rules that will help simplify finding derivatives. So first, we start with the constant function, taking the derivative of a constant function. We've actually seen this a few times at the end of Chapter 2. A constant function has a graph that is just a horizontal line, and the slope of a horizontal line is 0. So therefore, the derivative with respect to x of a constant is equal to 0. And of course, this works with any independent variable. So the derivative with respect to t of a constant function is 0. Essentially, the derivative of a constant is 0. Then next, power functions. Here we have what's called the power rule. If n is a positive integer, then the derivative with respect to x of x to the n is equal to n times x to the n minus 1. Essentially, the original power n drops down as a coefficient, and then we decrease the power by 1. I did an example at the end of section 2.8 where we noticed that when we started with a cubic and took the derivative, we knocked the degree down by 1, and we got a quadratic. And then when we took the derivative again, the degree went down by 1 again to a linear function. So the power rule is saying, we've noticed this pattern, and now let's just make it a rule. And this can be proven using the derivative definition. So we also saw some other examples of this, like if we had a linear function f of x equal x, that's just a line. The slope of that line is 1, and the derivative, found by using the power rule, gives us exactly this slope as the derivative. So that's a very specific case of the power rule. Later in section 3.6 in this chapter, we will find that the power rule is actually true for any real number. So we don't have to just restrict it to a positive integer. Next is the constant multiple rule. If c is a constant, and if f is a differentiable function, meaning its derivative exists, then the derivative with respect to x of c times f of x is the same thing as c times the derivative with respect to x of f of x. Essentially, we can factor out the constant from the derivative. This goes back to how we could factor out a constant from a limit. The sum and difference rules. If f and g are both differentiable, then the derivative with respect to x of f of x plus g of x is equal to the derivative with respect to x of f of x plus the derivative with respect to x of g of x. And then in the same rule, or I should say in the same way, the difference rule, if f and g are both differentiable, then the derivative with respect to x of f of x minus g of x is equal to the derivative with respect to x of f of x minus the derivative with respect to x of g of x. Essentially, we can distribute the derivative across a sum or a difference. And that also follows from the fact that limits can distribute across sums and differences. So those last three, constant multiple rule, sum, and difference rules, those all follow from rules that we had established for limits back in Chapter 2. So let's use these rules to find a derivative. This comes from number 8 on page 180 from our textbook. The function is f of t equal to 1.4 times t to the fifth minus 2.5 times t to the second plus 6.7. So now this is different than the directions we had in Chapter 2. Here I'm not going to use my definition, using the limit as h approaches 0, etc. I'm just going to use these rules. So this is where we do want to pay attention to directions on, say, an exam. I will be asking you to find derivatives using the definition, but other times I will be asking you to use derivative rules that we saw in Chapter 3. So here I'm just going to take the derivative with respect to t of my entire function f of t, and that way we can see how these work. So first, I have a sum and a difference inside the parentheses. I'm just going to distribute my derivative to each term. And then after I've finished doing that, with the first two that I have a constant times a function, so like I have 1.5 times t to the fifth, and then I also have 2.5 times t to the second, I'm going to factor the constants out in those cases where I'm using the constant multiple rule. So first I used the sum and the difference rule. Now here's using the constant multiple rule. And then also, in the third derivative that I had listed, the derivative of 6.7, 6.7 is a constant. The derivative of that is just 0. There I'm using another rule that we had described above. And then finally, we can use the power rule. So 1.5 times the derivative with respect to t of t to the fifth. The power rule says take 5, the power, drop it down as a coefficient, and then decrease the power by 1. 5 minus 1 is 4, so we get t to the fourth. And then minus 2.5, and now I have to take the derivative with respect to t of t squared. And again, I get to use the power rule. The power, 2, drops down as a coefficient, and then I decrease the power by 1, so t to the 2 minus 1, that's just t to the first. And then all I have to do to finish up is just finish my multiplication. 1.5 times 5 is 7.5, and then I have t to the fourth, and then minus 2.5 times 2, which is 5t to the first, which I can just write as t. And that's it. I can't combine any terms because I don't have common powers with my t's in this last statement. So that's it. That's how those rules are used. There's all of them actually in one problem. As we get further along, you don't need to be splitting up your work this much, but I recommend as you're getting used to these rules, do this for a while so that you're used to it. But after a while, I'm not going to be expecting that you're writing this out this explicitly. Let's look at another example where it's a special case of using the power rule, where we've got something that will be using a negative and a fractional power. So that way we get used to this power rule for any real number. This is a little bit early. You won't see examples like this in the homework for 3.1, but this is just getting you used to the fact of what we will see with this power rule. So first of all, if I want to find the derivative of h of x, where h of x is equal to 1 divided by the fourth root of x, we do want to think, first of all, that when we have a root, like the fourth root of x, that implies a fractional power. So fourth root of x means x to the 1/4. That comes from algebra and pre-calculus. And also, if I'm dividing by a power of x, that's the same thing as using a negative exponent. So here's a little reminder of that fact. So then if I want to find the derivative of h of x, then that's the derivative with respect to x of x to the negative 1/4 power. So the way that this really works with the full force of the power rule that again comes later in chapter 3, it's the same pattern as what I saw before. The power drops down to become a coefficient, and then I decrease the power by 1. So I have negative 1/4 minus 1. Negative 1/4 minus 1 is going to be x to the negative 5/4 power. And for us, it is okay if we write things using negative powers, but if you wanted to write this by using a positive exponent, we would have negative 1 in the numerator, 4 in the denominator, and now we're just reversing what we've seen with negative exponents. This becomes x to a positive power in the denominator, and that's positive 5/4. So I just wanted to show you that so you can see how the power rule works with other exponents besides integers. So then example 6 on page 177. Here let's apply these rules to do something that we've been asked to do before. Find the points on the curve y equal x to the fourth minus 6x squared plus 4 where the tangent line is horizontal. So now remember, the tangent line, that will be an equation for a line, and it has a slope and a y-intercept. And if they're saying we want to know where is the tangent line horizontal, that means that the slope of the tangent line is 0. How do we find the slope of a tangent line? That's using the derivative. So this question is really, where is the derivative y prime equal to 0? So first we have to find the derivative. Y prime is equal to the derivative with respect to x of x to the fourth minus 6x squared plus 4. And again, we can distribute our derivative. By using the sum and difference rules. On the first derivative of x to the fourth, I can use the power rule. That becomes 4x cubed. On the second derivative that I have listed, I can factor out the 6. And then on the third derivative that I have listed, the derivative with respect to x of 4, that's going to be 0. And then finally, I can use the power rule for x squared, and I get 6 times 2x. And so what I get from my derivative is 4x cubed minus 12x. So then now that we know our derivative, where is it equal to 0? So I just set 4x cubed minus 12x equal to 0. And we solve this like we would have in an algebra class. We factor out 4x, and I get 4x times x squared minus 3. I can factor x squared minus 3, or I can just set it equal to 0, and I could use the square root property. So I set my factors equal to 0, 4x equals 0. That tells me that x is equal to 0. And then x squared minus 3 equals 0. That tells me that x squared is equal to 3, which tells me that x is equal to plus or minus 3. Or sorry, plus or minus square root of 3. So that gives us the locations. The tangent line is horizontal when x is equal to negative square root of 3, 0, and positive square root of 3. Tangent line is horizontal when x is equal to negative square root of 3, x is equal to 0, and x is equal to positive square root of 3. If you wanted to know the y values for that, you could plug those into your original function. So x to the fourth minus 6x squared plus 4, if we used negative square root of 3, we get negative 5 from that. If we used positive square root of 3, again I have even powers there, I'm also going to get negative 5 from that. And then finally, if we plugged in 0, I should be writing this is y equal to those values. If we plug in x equals 0, then I get y is equal to positive 4. So that gives us our coordinates, the x and y coordinates. The remainder of this section looks at exponential functions, and in particular, how do we find the derivative of exponential functions? This is mostly going to focus on the exponential function e to the x, but we do get a little bit of a foundation that will be answered later on in Chapter 3 about what's the derivative of any exponential function. So first, we start with defining the exponential base e, meaning the natural number e. One that we might have seen in pre-calculus is this. The natural number e, which you have on your calculator, you could type in that symbol for e, and if you need to, raise it to the first power, and you get that it's approximately 2.718. One way that we could write that is actually using limits. This might have been introduced in pre-calculus even if you didn't know what the limit was, because we would have had this idea of just if we had our input get very large. The limit as n approaches infinity of 1 plus 1 over n raised to the nth power is equal to e. When it comes to any exponential function, like f of x equal b to the x for any base b, they all pass through the point 0, 1, because any base to the 0 power is equal to 1. But how they do so will be useful to us. Meaning, with the different bases, how are they going through that coordinate? Do they go through in a steep fashion or in a shallow fashion? So let's see. Let's find f prime of x for f of x equal to b to the x using the definition. So here f prime of x is equal to the limit as h approaches 0 of f of x plus h, which is b raised to the x plus h power, minus f of x, which is b to the x, divided by h. Using rules of exponents, I can factor out b to the x, and I get the limit as h approaches 0 of b to the x times the quantity b to the h minus 1, all divided by h. Since this limit depends on h, we can actually factor out b to the x, because it remains constant no matter what h is. So our derivative is really f prime of x equal b to the x times the limit as h approaches 0 of b to the h minus 1, all divided by h. If we were to plug in x equals 0 here, we still find that b to the 0 is equal to 1. If we were to plug in x equals 0 here, then since b to the 0 is equal to 1, we get that f prime of 0 is equal to the limit as h approaches 0 of b to the h minus 1, all divided by h. Why are we bothering to plug in 0? We're thinking of the slope, meaning how is it crossing through at this point 0, 1 for our original function. Thus, if it can be shown that f of x equal b to the x is differentiable at 0, which we're sort of playing around with here, then it will be differentiable everywhere else by just multiplying that limit above, meaning this limit, by b to the x. This also means that f prime of x, the derivative of any exponential function, is really equal to the derivative evaluated at 0 times b to the x, the original function. Which means that the derivative of f of x equal b to the x is proportional to the original function itself. And that means the rate of change of any exponential function is proportional to itself. That's an important concept. It's telling us that the rate of change of an exponential function is just some number times the function itself. So finally, of all choices for what b could be equal to, the simplest in terms of differentiation is the one that gives us f prime of 0 equal to 1. And the base that does that is the natural number e, which gives us a new definition for the natural number e. E is the number such that the limit as h approaches 0 of e to the h minus 1, all divided by h, is equal to 1. The culmination of this whole discussion is this. The derivative with respect to x of e to the x is just the function itself. By using what I was talking about earlier of how the derivative is proportional to the function itself, the number that's hiding right here is that limit that I just mentioned. The limit as h approaches 0 of e to the h minus 1 divided by h is 1. So that's why the derivative of e to the x is just equal to e to the x. We get to figure out the derivative for other bases of the exponential function in a later section, but for now, that's the rest of what we learned in section 3.1. So let's just look at a few problems to finish up. So first, number 34 on page 180 of our book. Find the equation of the tangent line to the function y equal 2 e to the x plus x at the point 0, 2. So first we'll get to practice some of the derivative rules that we've learned, and also we're going to just remind ourselves of how to find the equation of the tangent line. So remember what we saw before, the point-slope form of this tangent line in general is just y minus f of a equal to f prime of a times x minus a. And also remember that a, that's just the x-coordinate of the point that we are focusing on. So in our case, that's just 0. And then also remember f of a, that's just a general notation for our function evaluated at a. So in this case, our function, we called it y, and then it's of 0. And you could, of course, use the equation that was given to us, which was 2e to the input, so e to the 0, plus x, our input, or just 0. But this just becomes 2. But remember, that was given to us as well. So don't forget about that. Those things are not so confusing. It is sort of just given to us when we have the point. So really, all we need to figure out is the derivative evaluated at a. So to do that, let's just find the derivative in general. So y prime. And we're not going to go through using the definition of the derivative like we saw back in chapter 2. Here we're just going to use the derivative with respect to x of our function and just use the rules that we've established in this section. So first I can distribute my derivative across a sum. So the derivative with respect to x of 2e to the x plus the derivative with respect to x of x. And then in the first derivative that I have listed here, I can factor out the 2. And in the second one that I have listed there, I can use the power rule, which would just be 1, that was the power that was there, times x to the 1 minus 1 power, or 0 power, which of course, this whole expression at the end here, that is just going to be 1, which we should again expect because the slope of just the function x is the number 1. And then finally, the derivative with respect to x of e to the x, we just saw, is itself. So this just becomes 2 e to the x plus 1. So then y prime of 0 will give us our slope. If y prime is 2e to the x plus 1, then y prime of 0 is 2e to the 0 plus 1, which is 2 plus 1, or 3. And so now we have our slope. So then the equation is y minus the y-coordinate of the point, f of a, or f of 0, which in this case is 2, equal to the slope, which we just found was 3, times x minus a, which again is just x minus 0. And if we simplify by getting y all by itself, then we get y equal 3x plus 2. And again, we could use point-slope form or we could use slope-intercept form. Either way is fine. All right, so then one final note for something that you'll see in the homework is this definition. The normal line to a curve C at a point P is the line through that point P that is perpendicular to the tangent line at P. So just as a little bit of an image to go along with this, let's say that this was our curve C. And let's say that the point P that we were talking about was here. The tangent line would be the one that just touches the curve C at this point P. So that's our tangent line. The normal line is the one that is perpendicular to the tangent line, which means it has to be at a right angle. So to find the equation of a normal line, you would go through what we just did in the previous example, find the slope for the tangent line, but then just remember that the slope of a line that is perpendicular to another depends on the original slope. So let's say that the slope of the tangent line is something like, let's not use C, let's say it's D divided by E. It's a fraction, it's a number. The slope of the normal line the way that you find that is just by taking the tangent line slope, reciprocating it, and then negating it. So perpendicular means that the slopes are reciprocals of each other, but also opposite signs. So opposite reciprocal is the idea with perpendicular slopes. So keep that in mind when you are taking a look at any homework problems that involve the normal line. We may see some other examples as we go on as well. And you will also start to see this stuff in physics, and also as you get to calculus 3, we'll see some more stuff about normal lines.